Okay, in this video we're going to pick up after I'm assuming you've watched a couple videos about calculus basics and derivatives and the power rule and all that good stuff. And we're going to just quickly run through that. I'm going to spend much time on it because I assume you've watched the Khan Academy videos or some other equivalent. So essentially the main line point of those videos is that the slope of a line is the first derivative of the equation that draws that line. So if you look here for a basic linear equation, 4x plus 10, if you make a bunch of x values and you plug x into the equation, you get a bunch of y values and you plot that, you get this line right here, which is a simple straight line. And if you take the first derivative of this equation, according to the power rule, you get 4. So 4 is essentially the slope of this line, and 4 is a constant because the slope of this line never changes for any value of x. So let's go to the next slide and take a look at a slightly different function here. So in this case, we've got the equation is 4x squared plus 10 equals y. And so if you, again, think a bunch of x values, you plug it into the formula, get a bunch of y values and plot it, you get this. F of x is the same as y. I should have technically written f of x up here. And the slope is the first derivative of this equation. So with the first derivative power rule, the 10 drops out, right? Because it's essentially 10 to the 1 power there. We just get rid of that, take it out. And then you multiply the 2 times the 4 and get an 8, and then you drop the power by 1. So x squared becomes just x to the first power, and we usually don't write the first power in there. So the first derivative, or y prime, is equal to 8x. And what that's saying is that the slope of the line tangent to this curve will be 8 times whatever the value of x is. So it depends on 8. And you can see that, right? At x of 0, if you made a tangent line and looked at the slope of it, it would be exactly 0. So x equals 0, you multiply 0 times 8, you get a 0. So the slope would be 0. If you go over here to 1, you can see the slope of a tangent line here. And I wonder if I can use a, if I can see if I can do a pen function. I don't know if this will work or not. No, it doesn't seem to want to work. I don't know. But anyway, you can envision a little line right there, just, just tangent to this line, to this curve. And the slope there would be around 8, right? And we can know that mathematically because if you plug in a 1 right here, the slope, it would be 8. So the slope varies. And the further away you get from 0, the more the slope of the tangent line gets. So over at 5, it would be 40, right? 8 times 5. So you can see then that that the slope of the tangent line varies depending on how far you are from the sort of the apex here, or the minimum of this line. So when this line's at a minimum, the slope of the line tangent to it will be exactly 0. And the further you are away from that, the steeper the slope will be with this particular equation. So now we're going to take a look at a graph of a log likelihood function. You can imagine the graph of the likelihood function is essentially the same. It's just in positive territory if you're talking about likelihoods. And we looked at that when we looked at the Excel sheet on brute force maximum likelihood. We computed it both ways, log likelihood and likelihood. And you can see the shape doesn't really vary very much. It both make a, kind of an inverted U shape here. So what we're trying to find, keep in mind, with the brute force maximum likelihood is we were doing exactly this graph. We were plugging in different theta values, and we're trying to find which theta gives the maximum likelihood or log likelihood to get the same theta, right? That's why you can do the log likelihoods instead. So what theta value gives you the maximum of this curve? So now that we know a little bit about calculus, you can see kind of where we're going with this. Over here, if we wanted to know where this curve was minimized, we could find the point where the first derivative, the slope of the line tangent to it, equals 0. So if we were to want to know where this y, 4x squared plus 10, is minimized, we could take the first derivative and set that equal to 0, because then we know that that's where the slope of the line tangent is equal to 0, and that would have to be, by definition, the minimum of this original curve over here. And we're going to do the same kind of thing with IRT. If we want to know what the maximum, where on theta this function is maximized, we can take the first derivative and conceptually set that to 0, and that would tell us where the slope of the tangent line to this curve is equal to 0, which we would know would have to be the maximum. And if we knew that, we could compute theta. So here it is kind of graphed out. This is the original log likelihood, and this is the first derivative of the likelihood. And the first derivative is the slope of this function, right? So you can notice a couple things here about it. When you're at the very maximum of this likelihood function, right, whatever theta you're at there, the first derivative equals 0. So what we want to know is, where does this first derivative equal 0? If we can find that, we'll know that we're at the maximum of this line. Another thing to note here, if you have underestimated theta, let's say we're looking at evaluating a theta of 0.5 in this case, which is an underestimate of the maximum. In that case, the slope of the line tangent here is positive, right? Because we have underestimated it. So if we draw a tangent line right here, that tangent line will have a positive slope. And if you look up here where we've actually graphed out the value of the first derivative, you can see it's in positive territory. On the other hand, if we have overestimated the ideal theta, let's say we're over here at 2, if we drew a slope of a tangent line here, or drew a tangent line and looked at the slope of it, it would be negative. And you can see that because if you go to 2, you can see the slope of the first derivative there is in negative territory. So for anything to the right of where this first derivative equals 0, anything to the right of this 1.5 theta, right, we have overestimated theta. And anything to the left of it, we have underestimated theta. And the first derivative will be positive if we are to the left and we have underestimated theta. And it will be negative if we are to the right and we have overestimated theta. So again, given that, all we got to do is to take the first derivative, set that equal to 0, and solve for it. And then we have what theta gives the maximum likelihood estimate. But there's a problem with that. And this would be easy to do if we had a linear function or a quadratic like we were looking at earlier. You know, if y prime, the first derivative, were just 2x plus 5, we could set that equal to 0, solve for it, and we would get, you know, two places here where y equals 0. If it were quadratic, it would be, again, pretty easy. So, you know, if this were the actual like nature of it, if this were the, you know, the first derivative, we could solve for that too using the quadratic equation. And I'm not going to go too much into that. The problem that we have is that the first derivative of the likelihood function is not easy to set to 0. You can't just set this thing equal to 0 and solve it like you could if it were like a quadratic function. That just won't work for us. So kind of keeping big picture, let me go back to this graph over here, right? If we want to know the max of the original likelihood function or log likelihood function, then what we want to know is where the first derivative of that function equals 0. Unfortunately, the formula for the first derivative of that function is complicated enough that you can't just set it to 0. It doesn't work. So to do this, we're going to use something called the Newton-Raphson procedure. And this has been around for a while. This is named after Isaac Newton in part. Sometimes it's just called the Newton procedure. But it's an iterative process that lets us solve an equation or get a value for an equation where we can't necessarily just solve for it. So this is what the formula looks like. What we're trying to do is we have an equation and we want to know what level of x results in a y value of 0, right? And that's the kind of the problem we're trying to solve in IRT. We want to know what level of theta gives a first derivative value of 0, because that will tell us where the original function has its maximum value, right? And in order to walk through this, we're going to take a look first at a relatively simple process. And we're going to use just a basic quadratic function here to kind of show you how the Newton-Raphson works, even though we could just solve this equation straight out. So here's what the Newton-Raphson looks like. We have an initial guess at the value of x that leads to a y equal to 0. And what we're going to do is we're going to subtract from it this correction function each time. We're going to iterate this procedure. So, so we're going to use the solve for y, right, the original function, and using that value, initial estimate of x. And then we're going to divide that by the first derivative of y using that value of x. And we're going to use that information in this formula then to revise our estimate of x. So let's take a look again for this formula down here, 2x squared plus 10x plus 5. And we're trying to find what value of x gives us a y value equal to 0. Now, since this is a simple quadratic function, we could just solve this, right, with a quadratic formula and find out what value of x gives a y of 0. All right, we could do that. We could set y, this function equal to 0, and then solve for x, and that would give us the value that we are looking for. There's actually two values. But we're not going to do that. We're going to use the Newton-Raphson procedure so you can see how it works. And first, I'll start by showing you the final kind of solution to that we're going to find here. So this is the original formula, y equal to x squared plus 10x, and that's graphed in red. And you can see that that function takes on a minimum value over here. But what we're trying to do is find out what value of it, um, at what value of x does y equal to 0. And in order to do that, we're going to take the first derivative, which is graphed here, this 4x plus 10, the y prime, and the final solution we're going to get to is an x value of negative 0.56351, which you can see is right here. So it's one of two, with this problem right here, one of two where the where the function crosses 0. And we're going to find that not by solving algebraically with a quadratic function, but using this Newton-Raphson. So let's get started with that. So here is again, the function we're using at y equal to x squared plus 10x plus 5. We want to know what value of x gives us a y equal to 0. And to do that, we're going to need also the first derivative of this, y prime, is equal to 4x plus 10 using that power rule. So let's start with just a basic guess of 1.0 for x. It could be any value, and the nice thing about this process is that it will give you the right solution eventually. The closer your starting value is to the optimal solution, the quicker it converges, but all the same, it converges relatively quickly in any case. So let's plug in an x value here, and let's solve for y given x equal 1. So 2 times 1 squared is 1, 2 times 1 is 2, plus 10 plus 5 equals 17. And the first derivative for x plus 10, where x is equal to 1, is going to be equal to 14. And so the ratio then is going to be this 17, right, y, over the y prime, which is 1 point, I'm sorry, which is 14. 17 over 14 is 1.21. So the revised estimate of x, where we're trying to find where x equals, it gives a, what value of x gives a y equal to 0, is going to be the old estimate minus this ratio, so 1 minus 1.21, which is negative 0.21. And now we do the same thing, but instead of using an x equal to 1, we're going to use x equal to 0.21. We plug it into this formula for y, and multiply that negative 0.21 squared times 2 plus negative 0.21 times 10, right, which is there, plus 5, and you get a 2.9442. And then you take that 4x plus 10 first derivative, and you plug negative 0.21 into it for x, and you get negative 0.84 plus 10 equals 9.26. And so the ratio here is 0.318. And so what we're doing now is we take this old estimate of x, the one we just used, the current one, and subtract from it this ratio of 0.318, and we get a negative 0.527, whatever. We're going to round that up to 5.28. So you take that negative 0.528, you plug it into here, you get 0.277. You plug it into the 4x plus 10 first derivative, you get 7.88. Compute that ratio again of that over that, and you get 0.035. And then you plug it into this formula, and you get a revised estimate of negative 0.563. Same thing. This time you can see y is getting smaller and smaller, so that ratio is getting smaller and smaller. And what you see is that we have convergence here pretty quickly, right? The first time in, our ratio, our kind of correction factor was 1.21, and then it went down to 0.318, and then 0.03, and then eventually close to 0. And this is a fairly efficient estimator, right? So it converges relatively quickly. And the beauty of this is we could have started out with an x equal to, 500, and we would have gotten, when we did this, a much bigger ratio here to subtract. And so the more you're wrong by, the more it corrects, essentially. And so you get a correct estimate relatively quickly, usually after 4 or 5 iterations max, sometimes less than that. So again, this is telling us that an x value of negative 0.56 gives us a y value of 0, and that's what we saw over here, right? So you can see how the Newton-Raphson is interesting because it tells us what value of x leads to y equals 0. So in IRT, the analogy here is instead of x, we have theta, right? What theta value give us a likelihood equal to 0? But we don't really deal with the likelihood or the log likelihood equals 0, right? It never crosses 0. If you take a look back at that likelihood function, it's never equal to 0, either the log or the the regular likelihood function. This is the log here. What we want to know is not where the likelihood function equals 0, because it never does. What we want to know is where does the slope of the line tangent to this equal 0? In other words, where does the first derivative equal 0? So instead of solving for y, the x where y equals 0, we want to know what value of x leads to the first derivative, or y prime equal to 0. So that's a slightly different thing, right? So instead of using the equation like for the likelihood and the first derivative of the likelihood, we're going to use instead the equation for the first derivative and then the second derivative. So keep in mind, in the Newton-Raphson, if you want to know what value of x or theta gives y equal to 0, you use a Newton-Raphson. So what we want to know is what value of theta gives the first derivative equal to 0. So in the original Newton-Raphson, right, it was essentially like x here plus y over the first derivative. And what we're going to do instead is we're going to find where the first derivative equals 0. So we're going to use first derivative here divided by the second derivative. And to do this formula, we need to know the first and second derivatives. So the first derivative of the likelihood function is right here, right? It's this negative summation, right, across the items of a times u, which is either 1 or 0 for correct or incorrect, minus the p-value, right? So, so notice the subscripts here, right? I is items from 1 to capital I. That's however many items you have up here. So if you have 10 items, it goes from 1 to 10. And u is going to be for the given subject, right? That's what S is, subject for the given item, right? Was this item for this person correct or incorrect, 0 or 1, minus the probability of getting the item correct for that person, for that item, given that person's theta, right? So that's just the p-value we looked at all semester long. So that's the formula for the first derivative. And then for the second derivative, it's the sum across, and so you compute this for each person, for each item, right? Or in this case, we're talking about just one person, right? So you're just, we're solving for computing theta for one person. So it's just one person here, but you do it for each item, you compute all this, and then you take the sum across those items and then you multiply it by -1 to get the first derivative. And then over here, you compute the second derivative as a squared times p times q, right? Where p again depends on theta and whatever theta estimate you're looking at, and so does q, and then you're summing it across items, and that's the second derivative. We're going to walk through that in some detail here in just a little bit. So the reading, the Basics of Item Response Theory book from Baker, does a really good job of walking through this, and I'm going to show you what that looks like. But there's a difference in what Baker's doing. So he's not using he's not using a negative for the first derivative. He's using a positive. So as a result, he ends up adding right here instead of subtracting like the traditional Newton-Raphson, right? So keep that in mind. That is confusing as all get out. But we're going to look at that in a little bit of detail. Okay, now that we got the basics down, let's take a look at the example in the Basics of Item Response Theory book, which I think is a really nice summary. And just a reminder again that they're not using the kind of the true Newton-Raphson, where you've got the old estimate, which then you subtract out the correction factor. They're actually using a plus, and the reason is they're just using a positive for the first derivative. So instead of taking the negative of that and then subtracting that ratio, they're just keeping that positive. So it works out to be the same, but it is a little confusing when you look at it. And some people have it as subtracting that ratio, and other people have it as adding, and it can be a little confusing there. But technically speaking, the Newton-Raphson, as we saw in the example with the quadratic function, is you subtract that ratio, to get the new estimate, and they're not doing that. And the reason why they're not doing it is again because they're not using a negative for this a times u minus p first derivative here. So let's take a look at the one in the reading. I think it's really useful. I went ahead and wrote the item response parameters here, or the item parameters in. A parameter and the B parameters, so you can see what those look like. And you can see the math's pretty easy. I mean, you just take the observed response, you compute the p-value for whatever theta you're talking about. In this case, we're using 1.0. So that's the p with a theta of 1.0, and that's the q, so 1 minus p. And then you take that 1 times a quantity of 1 minus p, which is just q. No, it's not Q. I'm sorry. It's just, well, actually in this case it is Q, but normally it's just the 1 minus the p-value there, 0.19. And then the second derivative is just the a squared, so a parameter, which is 1.0 squared times p times q is that number. And you do that for all the items, and then you just sum that column for the first derivative. And the second derivative, you correct your estimate. And just like we saw earlier, in the example we walked through, you see the correction factor tends to get smaller and smaller each time, right? So the first time through, the correction factor is negative 0.773, then it's 0.097, then it's 0.009. It's a very efficient estimator. Also wanted to walk you through an example I've got here in Excel because I think it's useful as well. And what I've got here is got all the formula you need written down over here. And over in this section, I've got the pattern of responses, the item parameters, A, B, and C parameter, and this showing you how this process works. So again, you start with an initial theta value. I'm going to use just 1 here. And then you've got the correct or incorrect, which we're just copying from up here. If you look at this formula, the p-value just references the item parameters and that initial theta. And then the q is obviously just 1 minus p. And then you take that a, which is just the a parameter for that item. And if you click it here, you can see it's the a parameter, and then the u value, which is just correct or incorrect score, minus the p-value. And you do the same for the a squared times p times q. And you get all that, then you just sum up this column and you sum up that column. And I will say that here I did add a negative in front of that sum, so I am using kind of the traditional formulation here for the first derivative. So there's a negative snuck in there on you. And this ratio is one over the other, and then again you're subtracting out that negative ratio, which is serving to add a value here. So that's kind of what it looks like. Again, the ratio is going to be, it's going to be negative in this case because we have underestimated theta originally. So we're subtracting a negative, get an increase. And then I'm just copied that down here and done the same thing. Everything works exactly the same. The difference is now the p-value is computed with the new theta, right? It's not using 1.0, it's using the 1.88 from over here. And you get new values for p and q and all these things, but the process works the same way. You sum this up, you sum that up, and you see the ratio gets smaller and smaller again. And that keeps happening until eventually it just converges. It stops changing. And that's your final estimate of theta. So you can see it's a really efficient estimator. It's way easier in some ways. I mean, the math is harder, but it's a lot more computationally efficient than trying out 1,000 different levels of theta and then picking the max in that range. Right now, something like Excel would make that process pretty easy, but keep in mind this came around in the 60s when people were using punch cards and whatnot and very rudimentary computers. So having a process that converges relatively quickly was a very big advantage. So in this slide, it's a little bit confusing when you first look at it, but it's a graph of all these different things, right? So the theta is on the x-axis, and the likelihood function we've been looking at since early in the semester is here in the black. It's actually a log likelihood, so it's negative, but it's got more or less the same shape. And again, wherever this line is maximized is the same point on theta as when the regular likelihood function is maximized. So what we're trying to do is we're trying to find the maximum point of this black line, right? That's our goal. And to do that, we need to know where the first derivative equals 0. So we can compute the first derivative here, but unfortunately, you'll remember we can't just set that equal to 0 because the formula is too complicated. You can't just solve it for 0. So we use that Newton-Raphson where we try to figure out where the first derivative equals to 0. And to do that, we have to compute the second derivative. And so I've graphed all these things out here. What you'll see in this graph is that this slope here, right? The slope of the tangent line here is, it's positive if you've underestimated theta, so your first derivative is in positive territory. And if you're over here and you overestimated theta, your slope of your first derivative is in negative territory. And then the second derivative is kind of looks like this, right? It's kind of it's essentially the slope of the first derivative. And you can see the slope of the first derivative tends to be negative, right? So it's always negative over here, and it sort of levels off a little bit. And you see that reflected in the second derivative there. So as sort of a summary of what we're looking at there, when the first derivative, when theta is underestimated, the first derivative is positive, the second derivative is negative. All right, so this is going to be a positive slope here. The first derivative is in positive territory, but it's trending downward, so the second derivative is going to be negative. And then what we're doing with the formula is you get a ratio then where it's positive in the numerator, that's the first derivative, and it's negative in the denominator, that's the second derivative, and then you end up subtracting a negative value and increasing your theta estimate. And just like before, the further off from theta you are, the bigger the correction factor, right? So if you're way over here, you get a fairly steep slope right here, and you get a bigger correction factor because that's the numerator of that first derivative. And if you're pretty close to it, you get a relatively small slope, so you've got a much smaller correction factor. So that's what we mean by it's an efficient estimator. It's the amount of you're correcting by more the further off you are. So you sort of you can be wildly off with the first guess. And so long as there's a simple, single maximum with this original likelihood function, you should be able to find it with this maximum likelihood process. And this is the way actual maximum likelihood estimation works. This is it, right? It uses this Newton-Raphson. It's an iterative process. When you see other software like M+ and things for structural equation modeling, go through these iterations. It's doing a very similar kind of thing. It's trying to find the maximum point on some kind of likelihood curve like this. Okay, so let's take a look at that second derivative again. This is what it looks like. Again, it's a sum of across the items of a squared times p times q, and it should look a whole lot like the two-parameter model item information, which was a squared times p times q, right? So the information function is just essentially the sum of that across the items. So, which is a lot like, obviously then it's going to be pretty much identical to the test information function. So that's an interesting thing, and we'll take a look at why that's the case here in just a little bit. But it should look very familiar because again, it's essentially the same as the item information function here. Okay, so the larger the absolute value of the second derivative, the more peak the likelihood function is, less the more information. Let's take a look at that on this graph. So over here on the left, we've got a series of curves, like I showed you earlier, for the A parameter for all the items is 1.0, and over here on the right, the A parameter for all the items is 2.5, so much higher A parameter. So let's see what this looks like then. Again, the log likelihood function itself is this line right here, and over here it's this black line right here, and you can see it's got a much sharper peak on it over here because we have more information from the items. You get a much sharper peak, whereas over here it's relatively flatter. And what that means is that it's easier to find the top of the peak when you have a relatively sharp peak, right? Because typically speaking, and it's not too bad with this likelihood function, but when you talk about some of the other things like the C parameters, likelihood function, it's almost flat. So it's kind of hard to find the exact top of it. But here you see you get kind of bigger corrections for being less off, right? So if you have a theta of 1 over here, the slope of the tangent line is going to be more positive than it would be if you were at a theta of 1 over here, right? And it looks like the maximum likelihood estimate is around 1.5 here in these graphs. And you see that reflected, the slope of the line tangent to the likelihood function is reflected in the first derivative. And you get a much steeper slope for the first derivative over here on the right, that blue line, than you do over here on the left. And as a result, the second derivative, which is the slope of this first derivative, tends to be much more negative over here, right? And the standard error is correspondingly lower as well. So that's just a kind of look at how item information is reflective of that second derivative that we see in actually in this particular paradigm here, looking at the maximum likelihood estimate. So again, a flat log likelihood function generates a first derivative that hovers near 0 and a second derivative that does the same, and it can be kind of difficult to find there.